Okay. So let's start for today. So today we'll solve the linear algebra assignment for the previous round course. Okay. So let's come to the first question. Consider the matrix T with respect to same basis beta beta. The linear transforms T from P to R to P to R given by T of Px equals to Px minus P dash x with respect to the basis B equals to 1x x square. And the matrix is given. You have to find the value of the A and the B, C for the problem 2 and 3. So what it is given, T P2R the set of all polynomials with real coefficient degree 2 less than 2, right? P2R, T is the map. How it is defined? T of P of x, it takes polynomial and just send it to Px minus P dash x, right? Derivative of P. So we have to find the matrix of the T, and basis is given. Beta is the basis. What is it? 1x and x square. So how to find the matrix of T? So just see what will be the image of T under x and x square and write down the in column wise. So T of 1, what it will be? It will be 1 minus Px minus P dash x, it's 0, right? So it's 1. Now T of x, what it will be? T of x will be x minus x dash, it is 1, right? So x minus 1. T of x square, it's x square minus derivative of x square is 2x. So this we got. So how to find the matrix? So the matrix will be T with respect to this basis T beta beta. Sorry, let me write it. So we have to write this, we have to write in terms of basis. So means 1 dot 1 plus 0 dot x plus 0 dot x square, right? This how to write is minus 1 dot 1, right? Plus 1 dot x plus 0 dot x square. How to write this? So this we can write 0 dot 1 minus 2 dot x plus 1 dot x square, right? So what will be the matrix? So matrix of T with respect to the basis beta beta will be, so it is 3 cross 3 matrix. We have to write down in terms column wise. So first it will be 1 0 0, then it will be minus 1 1 0, and the next it will be 0 minus 2. It's a tutorial. I have a tutorial. I have minus 2 and 1. So this will be the matrix with respect to the basis beta beta. Fine. So and what it is given? Given that T is 1 0 A minus B 1 0 0 minus C 1. So what will be the value of A? So the value of A, because A is here, A, so the value of A will be, the value of A is 0, right? Because so as this is the matrix, A is here, so the value of A is 0. Now, so the question number 1 is done. So let's move to the question number B. What it is saying? You have to find the value of B, means where T is as early. So B is here. So minus B is here. So value of B, what will be the value of B? So it will be 1, right? Because here it is 1. So value of B is 1, right? as t is what? T is one zero zero minus 1 1 0 0 minus 2 1. So this is the minus b, right? So the value of b is 1. Now, so the question number 2 is also easy. So now move to the question number 3. You have to find the value of c. So let's see where c is. So t, as again, what is t beta beta? It's 1 0 0 minus 1 1 0 0 minus 2 1. And where is c? C is here, right? So let's see what will be the value of c. So as minus c is there, so value of the c will be 2, right? So question number 3 is done. So let's move to the question number 4. Okay, again it is the same question, means now it is from t is mapped from P3R to P3R, and t is given and two bases are given, and with respect to we have to find the just matrix, then you have to find what will be the unknowns. So let's first find what will be the matrix. So t, how it is given, t from P3R to P3R. And how this will map, what is the definition? T of summation ak x to the power k is summation ak x plus 1 whole to the power k. So this is the definition. Now you have to write down t with respect to the basis beta gamma. So you have to just apply the basis of t, and you have to write it in terms of the basis of gamma. So just first apply t of 1. So what will be the, so it is correspond to x to the power 0, right? Only the a to the power 0 will remain. So note 1 is, you can write a0 x to the power 0 plus all other are 0, right? So a0 is 0 here. So a0 is 1 into x to the power 0, nothing, right? 1 you can write it like this. So how it will map? So it will map 1 like this, because a0 only the non-zero term, and other will be 0, and x plus 1 whole to the power 0 into x plus 1 whole to the power 0, right? So this is again 1. Now what will be the t of x? T of x, so x to the power 1, so x is x to the power 1, so it will map to 1 into x plus 1, right? So, and what will be the t of x squared? T of x square will be 1 into x plus 1 whole square, right? So this will be the t of x. What will be t of x cube? T of x cube will be 1 into x plus 1 whole cube. So this will be the mapping image of 1x x square and x cube. Now you have to write this right hand side of this, what we have got, in terms of the basis of gamma. Then we will get the basis of matrix form of t with respect to beta gamma. So you have to write in terms of 1 gamma, 1 plus x square plus x cube. So how to write this? Just let me write here. 1 is x to the power 0. So what will be there? We have to write it in terms of, so 1 is 1, just you can write 1 plus 0 into 1 plus x plus 0 into x square plus 0 into x square plus x cube. 1 dot x plus 1, how can you write? 0 into 1 plus 1 into x plus 1 or 1 plus x, this does not matter. 1 plus x plus 0 into x square plus 0 into x square plus x cube. Now x plus 1 square, just expand it, what it will be? X square plus 2x plus 1, how to write? So 1 dot 1 plus, this you can write 2 into x 1 plus x so this is right minus 1 dot this 2 into x plus 1, so this is the same, right? Plus 0 into x 1 into x square (1 into x square) plus 0 into x cube, right? So you have write it like this. And how to write this last one? Just expand it. So it will be x cube plus 3x square plus 3x plus 1. So you have to write it in terms of the, so just how to write this? Minus 2, just let me write it and then explain what's happening. Plus 2 into x square plus x cube plus x square. So we have to write in terms of the basis of this, right? So we have, because x cube is there, we have put 1 into x cube plus x square, then x square, 1x square is gone, so 3x square is there, so we have put 2 dot x square, 2x square here. Now we have to write in terms of the basis x plus 1, so we have to write 3 into x plus 1 and 3, 1 is there, so minus 2 is extra, so just write minus 2. So minus 2 means, so this you can write minus 2 into 1, right? So all of we have written in terms of the basis 1 plus x, x square and x square plus x cube. So then the matrix of T with respect to the basis beta gamma, it will be, just write in the column wise, right? So first 1 0 0 0, the first column will be, so first column 1 0 0 0, the coefficient of the expression of this, right? 1 0 0 0, next it will be 0 1 0 0, so the next column will be 0 1 0 0. Now what will be the third column? It will be minus 1, so let me write it in color, minus 1 2 1 0, minus 1 2 1 0, so it will be minus 1 2 1 0, right? What will be the next one? So the next one, it will be minus 2 3 2 1, minus 2 3 2 1. It will be minus 2 3 2 1. So this will be the matrix of T with respect to the basis beta gamma. Now we have to find the unknowns, what it is given. First you have to find the value of A41, right? Fourth row, first column, so it is 0, A41 is 0, right? So A41 is 0, right? A41 is 0. A41 is 0. What is the next question? A23. What is A23? In second row, third column, it's 2. So A23 is 2. Right. Now what is the next question? A32. What will be A32? Third row, second column. Third row, second column, it's 0. So it's 0. A32 is 0, right? Now what is the next one? A12, A13, A14, A24. A12, A13, A14, A24. So what is A1 first row, second A12 is 0, A13 is -1, A14 is -2, and A24 is 3. So just sum it all this. So A12 is 0, A13 what it's -1, A14 is -2, and A24 is 3. So sum all this, what will be? A12 plus A13 plus A14 plus A24. So 0, -1, -2 plus 3. So it is 0. So we get the value of this is 0. Right? So question number 7 is done. Now move to the question number 8. Okay, so question number 8, what it is saying? Let B be a finite dimensional vector space and S and T are two linear operators on B. Which of the following statements are true? So S and T are two linear operators on B. Right. Now if S is injective, then ST is injective. So I have to show that if S is injective, then ST is injective or not. So we will show that this is not true, means we will give a counter example. So first option, S is injective. So let's take S from R2 to R2. So because these are linear operator, we have to define. So it's enough to define on the basis, right? So I will say, so S, just send what is U1? U1 is 1 0 and E2 is 0 1, right? These are the standard basis vector for R2. So we have it's enough to define on the basis, right? The operator, then we can extend it linearly. So define S of 1 0 is 1 0 and S of 0 1 is, now define it to be 0 1. So right, because so this maps basis to basis, so this is an injective map, right? Basically this is S is the identity map 1 0 0 1. So this is the identity matrix. So this is injective. So S is injective. Now we have to define a map T so that ST is not injective, right? Means we will disprove this. So now let's define. So let we have taken, now define. I will define, let define T also from R2 to R2. So there basically we want to map here what we have done, basically one basis vector. So this here what we have done, U1 to U1, basically E1 maps to E1, right, and E2 maps to E2, here we have done. So here we have done, so that because the basis maps to the basis, so means this is injective. Now here will map E1 will map to the E1 and E2 will also map to E1, right? So what we have done, E1 E2 both map to E1 we have done. So this is our TA. Then what will be the ST? So ST, what is ST? ST, so it means it is the composition, right? So ST is S composition T. So it will map from again. So first T will send R2 to R2. Then again S will map from R2 to R2. Right? So S compose T is a map from R2 to R2. So what will be the then? So S compose T of U1, what will be the S of T of U1? What is T of U1 is U1, right? And what is S of U1? S of U1 is U1. So this, and what will be the S compose E of E2? T of E2 is E1, so this will be E1, and S of E1 is E1, E2, right? So we have defined it wrongly. Let's change it. Then change the definition little bit. So just define it like this, because here this will become injective, because U1 goes to U1 and E2 goes to E2, so it will become injective. So you have to define in such a way so that ST is not injective. So that ST is injective, right? So you have to map T as injective. So just map it to R2 to R3, then where it will go. Oh, sorry, S of U1 is U1, right? Oh, sorry, it's correct. S of U1 and E2, we have mapped it to 1, 0, right? Sorry. Now what is S of U1? S of U1 is not E2, right? S of U1 is U1. So it's correct. So S of U1 is again U1. So both the map S composed T both map U1 and E2 to U1, right? So it is not injective, right? Because it's S of T1 it's mapped to different vector to the same vector. So this means S composed T is not injective, right? Which implies S composed T is not injective, right? So the option number 1 is false. So S is injective, but S composed T may not be injective. We have shown a counter example, right? Here S is injective, but S composed T is not injective. Now move to the next option. What it is saying? If T is surjective, then T compose S is surjective. Again we show that this is not true. So we have constructed examples either T is surjective and T compose S is not surjective, right? So option number 2. So what we have to, T is surjective first, so let's define S from R2 to R2 again. How we will define? E1 will map to E1 and E2 will map to E1, and define let's T R2 to R2. I will, because we have to make T surjective, right? So we will define E1 goes to E1 and E2 goes to E2. So note that so this is defined linearly. So for any vector it will be written in terms of E1 and E2. So it has a pre-image, right? So it implies T is onto, right? T is surjective means onto. Because any map it will be either linear combination of E1 and E2, and both E1 and E2 we can have a pre-image. So T is clearly surjective. Now let's compute what will be the TS. So TS means it is the T compose F, right? T compose F. So T compose F, it will be mapped from again R2 to R2, because both are mapped from R2 to R2. So what will be the T compose E of T compose S of E1? So T of, what is S of E1? S of E1 is E1, and T of E1 is, we have defined to be E1. So T compose S maps E1 to E1, and T compose S of E2. S of E2 is E1. So T of U1, and what is T of U1? It's again U1. So you see that T composites map U1 E2 to U1. So if you take the E2 vector, there is no pre-image, right? So not E2 in R does not have any pre-image. Does not have any pre-image. Any pre-image under T composes, right? So T composes is not onto, which implies T composes is not onto, not surjective or onto, right? So we have seen that if T is surjective, then T composes may not be surjective. So the second option is also false. T is surjective, then T composes may not be surjective, right? So option number 2 is done. Let's move to the option number 3. What it is saying, if T is invertible, then T inverse is linear and is invertible with T as its inverse. Okay, let's see. Option number 3. Given that T is invertible, given T is invertible, right? What is the meaning of this? Means that because T is the linear operator, for linear operators it is called invertible if, which implies there exists a linear map S. Suppose T is from B to W, B to V, it will, because it should be self map, right? Let's say then S, again we will get a map from S from B to B such that T composes and S compose T is identity, right? So invertible implies so that we get a linear map from B to B such that this will hold, right? And as given T is linear, so, and we call this, let's denote S to be T inverse, right? You have denoted S to be the inverse just by T inverse, what we have got. So by definition T inverse is linear, right? So by definition T inverse is linear, right? Now what we have to check that T inverse is again invertible and T as its inverse, right? So means we have to, so T inverse is invertible means we have to check that T inverse is 1 1 and 1 2, right? Now we have to check, use invertibility means 1 1 1 2. So to prove that T inverse is invertible, we have to check that T inverse is 1 1 and 1 2. Now we have to show, to check, to show T inverse is invertible, we have to show that T inverse is 1 1 and 1 2. So let's check first 1 1. T inverse is 1 1. So how to check this? So you have to take two vectors. Suppose T inverse is V1 is equals to T inverse of V2. We have to show V1 equals to V2, right? Then T inverse will be 1 1. So then apply, so let this, right? So then apply T both sides. t inverse of v1 equals to t inverse of v2. Then what will be the t compose t inverse? So it is t compose t inverse, right? v1 equals to t compose t inverse of v2. Now you know t is invertible, so t compose t inverse, this is identity, so means this is identity, so I v1 equals to I v2, so this is same as v1 equals to v2. So we have start with t inverse of v1 equals to t inverse v2, we have got that v1 equals to v2, which means t inverse is 1 1, right? So we have got that t inverse is 1 1. Now let's check t inverse is on 2. So you have to check t inverse is on 2. So t inverse is a map from B to B. So now you have to take a vector in the codomain, we have to find an inverse, right? Pre-image. So let's take, let V in B, then you have to find a pre-image, right? So we know that, we also know where the map will take T of B. So T of map where it will map, T of B it will map from, so as T is a map from B to B, so which implies T of B belongs to B, right? So we claim that this T of B will be the pre-image of B. So then T inverse of T of B means T inverse compose T of B, which is B, right? So which implies T of B is the pre-image of B under T inverse, so which implies T inverse is onto. So you have shown T inverse is 1 1 onto, so T inverse is invertible, which implies T inverse is invertible, right? Then it will must satisfy, so implies there exists a linear map, some, let's say L, such that T inverse compose L equals to L compose T inverse equals to identity, right? But you know that T inverse is unique, right? But we also have T inverse compose T equals to T compose T inverse is identity, and as inverse is unique, so L must be T, right? As inverse is unique, which implies inverse of T inverse will be T, right? So we have proved it, that T inverse is invertible and inverse of T is T. So this is correct, option number 3. Now move to the option number 4. What it is saying? If S and T are invertible, then ST is invertible, right? So you have to check ST is invertible, means we have to check ST is 1 1 and on 2. So given S and T are injective, invertible, right? Invertible. we have to prove that ST is invertible. So to show S compose T is invertible, in order to show that, we have to show that ST is 1 1 and 1 2. So let's first check ST is 1 1. ST is 1 1. Means again the same, we have to take two vectors such that ST of B1 equals to ST of B2. So let ST of B1 equals to ST of B2. Now you know that S is invertible, right? So S is 1 1. So which implies T of B1 is T of B2. Why? Because as S is 1 1. Right. Now again you know that T is invertible, means T is also 1 1, which implies B1 equals to B2 as T is 1 1. So you have got B1 equals to B2. So this is the same as saying ST is 1 1, right? So this is done. Now you have to do the what, we have to check that ST is 1 2, right? So let's check ST is 1 2. So how to solve where? So let's first see where the map. So let's so T is suppose T is a map from U to V. T is a map from U to V, and suppose S is a map from V to W. Then ST will be mapped from where to where? First U to V and U to W, right? So basically this U to V, this is T and this is S. Now so ST is on to means we have to take an element from W and we have to find a preimage in U. So let's take a small w in capital W, right? So now you know S is invertible, means S is on to. So by this, so you have taken an element from here. So as S is invertible, we get an element V in here. So as S is on to, which implies there exists a V in capital V such that S of V will be W, right? So you get an element in here V. Now again you know T is onto, so again, so now as T is onto, which implies there exists a U in U such that T of U is V. So now let's compose S compose T of U. So then S T compose U, what it will be? S of TU. What is TU? TU is V. What is S of V? It's W. So see that ST maps U to W, means U will be the preimage of W, which implies U is the preimage of W. So ST is, so this is the same, that U is ST is on to, right? So we are done. So ST is invertible, right? Because we have shown ST is 1 1 and on to, so ST is invertible if both are invertible. Now what is the next option? You have to show that if S and ST are invertible, then T is invertible. So now let's check option number 5. S and ST are invertible given. So given S and ST are invertible. We have to show T is invertible. To show T is invertible. Okay, so means we have to check T is 1 1 and 1 2. So let's check first T is 1 1. So how to check T is 1 1? So take any two vector again. So take T of B1 equals to T of B2. Now you know ST is invertible, so apply S. So then what will happen? ST of B1 will be ST of B2, right? So which is same as ST is B1 equals to ST of B2. Now as ST is invertible, which implies B1 is B2, right? Because ST is invertible means ST is 1 1. As ST is 1 1, right? So you have shown T is 1 1. Now you have to check T is on 2. So we have to check T is on 2. So we have this U to V, this is the map T, and V to W, it's S, and ST is given. So T is on 2. Let's take a small V in V. You have to find a pre-image, some element U such that TU equals to V. Then let's define. So let S of V equals to W, small w, which will be in W, right? Because S is a map from V to W. So now what do you know also that S is invertible, right? So S is invertible means, so which implies V equals to S inverse T, right? As S is invertible, as S is invertible, as S is invertible, right? So V equals to S inverse W. And so where this W is in W, and now ST, what is also given, ST is invertible, right? ST is invertible means ST is on 2. Now W, small w belongs to capital W, and ST is a map from U to W, right? Is invertible. So which implies ST is on 2, right? So implies there exists U in capital U such that ST of U equals to W, right? And so which is same as S is invertible, apply its inverse both sides. So apply S inverse both sides. So which will imply that T of U equals to S inverse W, right? And what is S inverse W? We have shown that S inverse W is B. So which is B, right? T of U is B. So we start with a B and we find out an element U, small u in capital U, such that U is B. So which implies T is onto, right? T is onto, right? So you have shown T is 1 1 and onto, which implies T is invertible, right? Which implies T is invertible. So you have proved the option number 5. So option number 5 is true. So if S and ST are invertible, then T is invertible. Okay, now move to the next one. What is saying? If ST is invertible and S is injective, then S and T are both invertible, right? So ST is invertible and S is injective, then S and T are both invertible. Okay, so note that ST is invertible given, S is injective. If you show that T is onto, then T will be invertible. So now by the previous one, S and ST invertible implies T invertible, then we will automatically get T is invertible by the previous one. So it's enough to check S is onto, right? So let's write down what I am saying right now. So this is option number 6. So given ST is invertible, given ST is invertible and S is injective, we have to show, we have to prove S and T are invertible. Note that earlier we have shown that if S is invertible and ST are invertible, then T is invertible. So by 5, it is enough to show, it is enough to show that S is onto, right? Then because S is injective given, so then S will be invertible. And now by the fifth one, T will be invertible. And then using 5, as S and ST are invertible, which will imply T is invertible. So it remains to show that S is onto, right? So it remains to show. So then we are done. So it remains to show S is onto. So now let's check S is onto. So what it is given, S is injective and ST is invertible given. So S U to B, this is a map S and T is here, right? Oh sorry, T is here. So this is T is mapped from U to V, and this is a W, S mapped from V to W. You have to check S is onto. So let's take an element small w from here. You have to find a element which is in V. Take small w and w. Now you know st is invertible. So as st is onto, invertible means it's onto, imply there exists a small u in capital U such that st of u is w, right? So then what will be the preimage for w? Tu is whole, then not t of u, where tu is v, right? Then s of tu, what will be the s of tu? It is s composed t of u, so this is w, right? So tu is the preimage of w, which implies tu is the preimage of w, preimage of w under s. So which implies s is onto. So we are done. S is onto. So we are done, right? So option number 6 is also true. So this is also true. Option number 6 is correct. Now I have to check the last option. What is it saying? T is invertible if and only if rank of T is dimension V, right? So T is invertible if and only if rank of T is dimension V. So this is the 7th one. What is saying? T is invertible if and only if, what it is saying, in rank of T is V. Rank of T equals to dimension of V, where T is a map from V to V, right? So let's check. So T is invertible. So this side, first check this side. Assume T is invertible. You are proving this side. Assume T is invertible, right? Which implies T is 1 1, right? T is 1 1. And in the last class we have proved that if T is 1 1, if and only if nullity of T means dimension of the null space is 0, which implies nullity of T is 0. And but we know the rank nullity theorem, right? What is rank nullity theorem? By rank nullity theorem, what we know, that rank of T plus nullity of T is 0, right? Sorry, dimension of B. Sorry. So what is rank nullity theorem? Rank plus nullity is dimension of the V, right? So nullity is 0. So which implies if this is 0, rank T is dimension V, because this is 0 equals to dimension V, which implies rank of T is B, dimension V. So this we have to prove. So we have proved the forward direction. Now we have to prove the other direction. So now to prove the other direction, this direction. So here we will assume a rank of T is dimension of B. Now we have to prove that T is invertible, right? To prove T is invertible, right? And we also know that on the finite dimensional vector space, T is 1 1 implies T is onto, right, invertible. Now again use rank nullity theorem. Right. So what will be given rank of T is dimension B by rank nullity theorem? By rank nullity theorem, what it is? A rank of T plus nullity of T is dimension of B, right? What is given? Rank of T is dimension B given, or dimension B plus nullity of T is dimension of B. Now as dimension B is finite dimensional, because here we are dealing with finite dimensional vector space, so which implies nullity of T is 0. Why? As dimension of B is finite. Here we are only talking about the finite dimensional vector space. So nullity of T is 0 implies, by earlier exercise, that T is injective. T is injective, you can only dimension of the null space is 0. T is injective. And also it was done in the class that if T is injective implies T is invertible, which implies T is onto, right? It was done in the class on finite. So what I am telling it, what is on finite dimensional this is just the application of rank nullity. Finite dimensional vector space, T is 1 1 if and only T is onto. This is the application of rank nullity theorem. This was done in the class. So T is onto. So we have got T is injective and both onto, which implies T is invertible. Right. So you have proved that if rank of T is dimension B, then T is invertible. So you have proved the both parts. So you have proved the if and only part. So option number 7 is also correct. Okay. So question number 8 is done. So let's move to the question number 9. Okay, what it is saying? Let B be a finite dimensional vector spaces of dimension n over a field R, and let I denote the identity transformation on B, and In denote the n cross n identity matrix, and assume that beta and gamma are two different ordered bases of B. Which of the following statements are true? So 4 options are given. You have to find which one is true. So let's come to the first option, number 1. It is given B is finite. I is the identity transformation. What is meant by the identity transformation from B to B? So if it maps, if you take any value in B, it will map again B to B. So I of B is the B for all B in B, right? So this is the identity transformation. And what is the In? In cross n. So this is the n cross n matrix, means 1 1 dot 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 1 and all other are 0. So this is the In, right? So the matrix of the identity transformation is identity. So assume that beta and gamma are two different ordered bases. So which of the following are true? So I would do so that the matrix of I with respect to both the bases are same. So right. So let's take two bases. So let take beta equals to, suppose b1 dot bn, right? This is a basis, and gamma equals to dot wn. So these two are the bases, beta and gamma. Now we have to find the basis of I with respect to both the bases. So because I is the identity transform, means I of b1 will be b1, like that. So I of bn will be bn, right? So then what will be the matrix? So b1 you can write it as 1 dot b1 plus 0 dot b2 plus dot 0 dot bn, right? And so let's write the second one also. I of b2, what is I of b2 is b2, so this you can write 0 of b1 plus 1 b2 plus dot 0 dot b1. So like this way, I of bn, you can, it will be bn, so this you can write 0 dot b1 plus 0 dot b2 plus dot plus 1 dot bn. So what will be the matrix? So we know how to find the matrix with respect to given basis, beta beta. So just write down in terms of columns. So we have seen, just write 1 0 0 0 0 0 0. So this one will be 1 0 0 0 0 0, right? Next one, it will be 0 1, and again it will be 0 0 0 0 0. So we will get 0 1 0 dot 0, right? So like similarly, I will get the last one 0 0 0 0 0 0, last one will be 1. So it will be dot 0 0 0 0 0 0, last entry will be 1. So this is the n cross n identity matrix, right? So this is I n cross n. Now so we have find out I beta beta. We have to find I gamma gamma. So let's check. Now what will be the I of w1? This is identity mapping, means it will be w1. So just write down in terms of 1 w1 plus 0 w2 plus dot 0 w1. Similarly I w2, it will be w2. So this you can write 0 dot w1 plus 1 dot w2 plus dot 0 dot w1, right? So do the similar thing. So I w1, it will be w1, right? So it will be 0 dot w1 plus dot 0 dot w2 plus dot 1 dot w1, right? So again, if you write down the matrix of I in the ordered basis gamma gamma, so what you will get? So the first one, it will be 1 0 0 0 0 0 0. So this will be again 1 0 0. So the next column, it will be 0 1 dot 0, right? So it is 0 1 0 dot 0. And now do the same for, and what will be the last column? Last column will be 0 0 0 0 0 0 1. So it will be 0 0 dot 0 0, and the last entry will be 1. So again we see that this is the I n cross n identity matrix, right? So you see that both are same. So the first option is correct, right? So I with respect to both the bases are same. Why this becomes same? Because we are seeing identity matrix with respect to the same basis, beta beta and gamma gamma, right? Because beta we are not changing here anything, beta beta we are saying, so that's why we get the same. So the first option is correct. Now let's come to the next option. you have to find the identity matrix with the basis gamma and beta. So you have to check that is this identity matrix or not. So the option number 2. So you have to find the, yes. So you have to find the identity matrix. So we have so that this is in or not. So you show that this second option will be false, means if you write the identity matrix with different basis gamma beta, then it will not be identity matrix. Let's see by an example. So let's take gamma to be this 1 0 and 0 1. So these two are the basis of R2, and take beta, you will take 1 1 and 1 minus 1. So you can check that both are the basis of R2. So check just both gamma and beta are basis of R2. Now let's compute the identity matrix with respect to basis gamma and beta. So I of 1 0, so it will map to 1 0, right? Now you have to write down in terms of basis of 1 1, right? And 1 comma minus 1. So how do you write this? So you can write this as just half 1 1 plus half 1 minus 1, right? This you can write. And then what will be the I of 0 1? It will be, so let's define, so it is 0 1, right? Because this is the identity transform. So how can you write in terms of the basis of gamma? So this you can write half of 1 1 minus half of 1 comma minus 1. So then what will be the matrix with respect to the basis? Gamma beta. So it will be the so it will be the half means write down, it will be half, and what will be the next column? It will be the half minus half, right? So it will be half minus half. So this is the identity transform with respect to the basis gamma beta. So this is not in, right? N cross n identity matrix. So the option number 2 is false, right? So we got a counter example where this is not true. So this is false. Now what is the third option? It is saying that is the identity transform with respect to basis gamma beta is same as identity transform with beta gamma. So let's check again. We will show that this is also not true. So for 3 we have take the same basis and beta gamma, right? Take the same example as of 2. So we have already find I gamma beta, and now we have to find I beta gamma. So for that we will take the basis from gamma beta and we will map it to, so what is the basis of beta? 1 1 and minus 1 1. So 1 1. So here it will map, because it's identity transform, it will map 1 1. Now you have to write in terms of basis of gamma, means 1 0 0 1. So this you can write 1 1 0 plus 1 0 1, right? Now what will be the I of 1 minus 1? So this will be the 1 minus 1 because it's identity transform. Now how can you write this? 1 comma 1 0 minus 1, you can write 0 1, right? So then what will the then I of, so this is beta gamma, right? So beta gamma, what it will be? So it will be again 1 1 first column, so it will be 1 1. What will be the next column? It will be 1 minus 1, so 1 minus 1. So this is the matrix. So you can see that these two are matrices are not same. So I beta gamma is not equals to I gamma beta, right? So option number 3 is also false. Right. Okay, so option number 3 is also incorrect. Now move to the option number 4. So what is option number 4? It's saying that every n cross n invertible matrix can be realized as a change of basis matrix I gamma beta for some basis gamma beta. So means it's saying that means there exists some basis gamma beta in which any invertible matrix can be written as identity matrix with respect to that two bases. Okay, so let's prove this. So this is option number 4, right? So what it is saying? So let me write down the statement. Every n cross n invertible matrix can be realized as a change of basis matrix I gamma beta for some basis gamma and beta, right? So we have to prove this. So we will prove this statement. So let's prove. Suppose take any invertible matrix. So let A, which is this A11 dot 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 A1n dot 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 AN1 dot 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 ANN be an invertible matrix. Right. So then if you apply, suppose let's denote ek, let you want to be, this is the 1 0 0 0 0 0 1 at the ith place, right? What is e2? E2 0 1 0 0 0 0 0 0, right? Like this way. So what will be the ek? Ek will be 0 0 0 0 0 0 1 0 0 0 0 0 and 1 will be in the kth place, right? So these are the E1 E2 ek, right? So now apply A, apply on ek, right? What we will get if you apply A over ek? So this is A11 dot 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 A1n dot dot AN1 dot 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 ANN. So this you can view as a column vector. So this is 0 0 dot 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 0 1 0 dot 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 0. So this is n column vector, right? So these are just view as a column vector. So if you multiply this, so what you will get? So then you will get this, right? First you will get a1k dot dot dot, you will get a nk. So just you will k the kth column vector. So this is the kth column of the matrix A. Of the matrix A. Right. So like that. So A of ek maps the kth column of the matrix A. So now we will show that all the columns will be independent. So means they will form a basis. Now we claim that the column vectors, columns of A forms a basis of Rn, right? So there are n many columns. So if you show that they are independent, then they will be the basis of Rn, right? Because there are n many columns. So as there are n many columns, of A. So let's say V1 is the first column, A11 dot 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 A1n, like that dot dot dot. Vn is the last column, an1 dot 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 ann, right? So as there are n many columns of that, if they are independent, linearly independent, so if v1 dot dot vn are linearly independent, then they form a basis of Rn, right? So we will show that they are linearly independent using that A is invertible, right? Now suppose, so assume contrary that they are not independent, right? So if v1 dot 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 vn is not linearly independent, independent, then what will happen? Then there exists a1 dot 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 an such that a1 v1 plus dot dot dot, sorry, let's say some beta 1 beta 2 beta n, beta 1 beta 2 beta n. So beta v1 all are not 0 such that beta n vn equals to 0, right? So then what will happen? We have seen that A of ek is, this is the vk, right? As we have denoted, as we have A of ek is vk. So from here, so A of beta 1 e1 plus dot 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 beta n en will be beta 1 A of e1, right, plus dot 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 beta n A of en. So which means this is beta 1 a1 v1 plus dot 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 beta n vn, and which is 0, which imply a of this is 0, which implies a of beta 1 e1 plus dot 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 beta n en is 0, but a is invertible, but a is invertible, which implies this should be 0, right, because then the kernel will be the 0, right. So which implies beta 1 e1 plus dot 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 beta n en is 0, but e1 e2 en are all linearly independent because they are the basis for Rn, standard basis, right. So which implies, so but this cannot be true, so which is a contradiction, right. So which is a contradiction. Contradiction as u1 up to n are linearly independent, right. So our assumption is false, means this set b1 up to bn is linearly independent. So which implies b1 up to bn is linearly independent. So what we have shown? We have shown that the column vectors of A are linearly independent. So we have shown. Columns of A are form a basis of Rn, right. So they are now the basis of Rn. So let's call it what you denote. So let's call gamma. So let's call beta to be the standard basis, e1 up to en, and gamma to be this, b1 up to bn. So these are the column. So both are not, both are basis of Rn. So now let's compute the identity matrix with respect to the basis gamma beta. So then what will be the identity of v1? It will be v1, right, and this you can write, how you can write? So v1 is, what is v1? So v1 is a11 comma dot 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 a1n. So means this you can write a11 e1 plus dot 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 a1n en. So similarly, how you can write this? You can write that I of vn. So this is identity map, means vn, and which is this an1 comma dot 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 ann. So this you can write an1 e1 plus dot 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 plus ann en. Now let's write down the matrix of I with respect to this basis. So then I with respect to the basis gamma beta, right. So what will be, so basis will be, how you write? So it will be a11 dot 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 a1n in the first column, a11 dot 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 a1n. Like similarly you can do ann. So what it will be, the last column it will be an1 dot 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 ann. So it will get an1 dot 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 ann, right. So this is the matrix. So what it is saying, the question? So question was that any invertible matrix can be realized as the change of basis matrix gamma beta for some basis beta gamma. So we have found out two bases, gamma and beta. So we have found out this basis beta and gamma. So these two are the bases, beta and gamma, with respect to these two bases, the invertible matrix A. So this is exactly the invertible matrix A which we are starting with. So we have started with this A, so this A can be written as identity map with respect to these two bases. So we get that the matrix A can be realized as a change of basis matrix I gamma beta with respect to the basis what are the bases? We have taken gamma to be v1 v2 vn, the columns of A, and beta we have taken the standard basis e1 e2 en, right? So this proof is done. So you have shown that option number 4 is also true. Any invertible matrix can be realized as a change of basis matrix for some identity transformation gamma with some basis gamma beta. So question number 9 is also done. Okay, let's move to the question number 10. Okay, so it's saying that which of the following statements are true. It's saying that there is a natural isomorphism between two n-dimensional vector spaces over R. So what it is saying, the first option, there is two natural isomorphism between two any n-dimensional vector spaces over R. So let V and W be two n-dimensional vector spaces over R. Then so because they are both have dimension n, so they have, so let v1 vn is the basis of is a. So choose any basis of v1 is a basis of v1 v and choose a basis of w. Let w1 wn is a basis of w, right? Now you have to show that there is a natural isomorphism, means in a invertible linear map, so that this map v to w. So you have to find an invertible linear map. So what will be the natural candidate? So now let's define. So just map basis to basis. Define T from V to W. How you will define this? T of V. Just map V1 map to W1, V2 map to W2, Vn map to Wn, right? So then we have defined a map. So now, so this map basis to basis. So this you can easily check that this is a 1 1 and 1 2, right? Means invertible because this has dimension. So So this is just an easy exercise because it's map basis to basis. You can check that. You can check T is 1 1 and 1 2. So let me tell you how you will check. Just I will not write down. So because any vector, if you take onto, for that onto you have to check for any w and w there is a pre-image v, right? So if you take any vector in w, so it will be, it can be linear as a linear combination of w1 up to wn, right? And then just take the pre-image of suppose c1w and then c1 v1 c2 v2, so c and bn will map to that vector, right? So it will be t will be onto, and why it will be 1 1. So just check what will be the, what is in the kernel. So for that you can see using the linear independent of v1 v2 vn, you can show that kernel of t is 0, right? So t is 1 1 and 1, which implies t is invertible. So there is a natural isomorphism. So, and this is the natural, right? Because you have done nothing, you have sent just only picking two bases, you have sending basis to basis. So there is a natural isomorphism between n dimensional vector space. So the option number 1 is correct. So let's move to the next option. What it is saying? The linear operator LA corresponds to the matrix A is invertible if and only A is invertible. So write down just what is LA? LA is a map from Rn to Rn. How it's defined? LA of x, it's multiply A dot x. So this is the linear transform LA. It's defined by LA of x equals A dot, left multiplication by A, right? Now you have to check that LA is invertible if and only if A is invertible. So you will show that the linear transformation of LA means if you write down the matrix of LA, it will be A. So right. So let's say, so let A is this A11 dot dot dot, AN1 dot dot. Sorry, it will be A1n, A1n, AN1 dot dot dot, ANN, right? So you have to write down the, let's write down the matrix matrix of LA, right? So let's take the standard basis U1 U2 En. This is the basis for En. So how you will write down then what will be the LA of E1? LA of E1 will be A dot E1, right? So what will be the E1? So if you multiply this matrix with E1 means 1 0 0 0. So what you will get? A1 1 E1 plus A 1 2 E2. Sorry. E2 plus dot 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 A1 and En, right? So this will you can write. Similarly, if you write down LA of En, so this will be A dot En, so this will be A1 and sorry, so this will be A21 and this will be AN1 and this will be A1n dot U1 plus A2n E2 plus dot 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 ANN dot En. Then from that we can write down the matrix of LA, right? So if you write down the matrix of LA, Suppose this is beta, so just write down with respect to beta. So then what will be the matrix? So LA of E1, it will be A11, A21 dot AN1, right? So it will be A11, A21 dot AN1. What will be the next column? If you write down, it will be A12, A22 dot AN2, right? Like similarly, last column it will be A1n, A2n dot ANN, A1n, A2n dot ANN, right? So you have got, so this is the matrix we have got. Right. So now let's see that you can see that this is exactly the matrix what A, right? So this is the matrix A. So you have got that the, so LA with respect to this basis, beta is A, right? So from here we can say that because this is the matrix, if there is one-to-one corresponding between the linear transformation matrix, so if LA is invertible, if and only if A is invertible, so which implies LA is invertible if and only if A is invertible. Right. So option number 2 is also correct. Now let's move to the option number 3. It's saying that given any two non-zero vector v1 and v2, there is a linear operator on R3 such that T maps v1 goes to v2. Right. So what it is? Option number 3. So given any v1, v2 in R3, you have to find a linear transformation T on R3 such that this will map v1 to v2. So this v1 and v2 is given. So just extend it to the basis. So let take v1 and extend it to the basis of R3. Right, this is the extension theorem. We can always extend the basis. So what will be the, so let's say v1 w1 w2 be a basis of R3. Now we have to define a linear transformation. So it will enough to define on the basis, right? So define T from R3 to R3. How you will define? So just map v1 goes to v2 and all other you can map it to same, right? w1 goes to v2, w2 goes to v2. And you can check that this is a linear map, right? And extend it linearly. To whole R3, right? So get a linear transformation which map T of v1 to v2, right? So the option number 3 is also done, correct, right? Now move to the option number 4. It's saying that given a diagonal matrix whose diagonal entries are non-zero, there exists a non-invertible linear operator T whose matrix is A with respect to the standard basis. Right. So a diagonal A is the diagonal matrix with all the entries are non-zero. So you have to find a linear non-invertible. You are saying that there exists a non-invertible linear operator T whose matrix is A. So what it is saying, option number what 4. What it is given A is the diagonal matrix lambda 1 lambda 2 dot 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 lambda n, all other are 0, such that lambda 1 dot 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 lambda 2 non equals to 0, all are non-zero, right? So it's saying that does there exist a linear transformation non-invertible whose matrix is A, right? So this is the matrix and all the diagonal entries are non-zero. So what will be the inverse of A? Check that A inverse will be given by 1 by lambda 1, 1 by lambda 2 dot 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 1 by lambda n, right? So this will be the inverse. For diagonal matrix you can easily check. So then if you compose it, what you will get? A compose A inverse will be A inverse compose A will be identity matrix, right? So if there exists a linear, so if there exists T non-invertible such that the matrix of T with respect to some basis, suppose say alpha is A, then what happen? Then A will not be invertible, right? Then A is not invertible, right? Which is a contradiction, because A is invertible. We have shown that A inverse will be this. So means there does not exist any non-invertible linear map, so that whose matrix is A. So the option number 4 is false. There does not exist a linear map whose matrix will be that matrix A, right? Now move to the option number 5. Let T be a linear operator on R3 represented by the diagonal matrix A with respect to the standard basis. Then T is invertible if and only if the diagonal entries are non-zero. Okay. So what we have to prove? So this is option number 5. The T is invertible if and only if, or T is a, what it is given? So given that T some standard basis, suppose beta, it's A, where A is lambda naught to lambda n, diagonal matrix, where beta is, suppose this is the standard basis. Then we have to show T is invertible if and only if diagonal entries all are non-zero, right? So we have proved that if all the diagonal entries are non-zero, then A is invertible, right? So this is the reverse direction by 4. If all the diagonal entries are non-zero, then T is invertible, right? Means A is invertible, which is same as T is invertible. Now you have to prove the forward direction. Means if T is invertible, then all the diagonal entries should be non-zero. So assume T is invertible. So we have to prove all the diagonal entries are non-zero. So suppose let's say, it's on R3 it's given, right? So we do not need to do for all. In R3 it's given, so it's in R3. So lambda 1, lambda 2 and lambda 3. 0, 0, 0, 0, 0, 0, and the basis is En. Means this statement is true for Rn also, not R3. So beta is E1, 2, E3. Right. Now what happens if some entries are 0? So let's say without loss of generality, suppose, so without loss of generality, let's say lambda 2 is 0, right? So if all the entries are non-zero, then we are done. So suppose let's say lambda 2 is 0, then what we will check? So means then check A of E2, right? A of E2. So what is A? Lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. Apply with this 0, 1, 0, right? Then what you will get? 0, it will be, so this is 0. 0, 0, because lambda 2 is 0. So 0, 0, 0, this is 0. So you get A of E2 is 0, right? So which implies E2 belongs to the kernel of A, right? So it means that nullity of implies nullity of T is a non-zero, right? So which implies T is not 1, 1. T is not 1, 1. Which implies T is not invertible. But this is a contradiction, right? It's given T is invertible. So means there cannot be element in the diagonal which is 0. If some element is 0, then we will get a contradiction. So which implies all lambda 2, lambda 3 are non-zero, right? So we have get that the option number 5th is also correct. T is in, if A is a diagonal matrix, then T is invertible if and only if all the diagonal entries are non-zero. So this is correct. Oh sorry, the last option it was incorrect, right? We have done it. Because option number 4, yeah, then A is not invertible, right? No, 4 is correct. Incorrect. Okay. So this was done. So now let's move to the question number 11. What it is saying? Which of the following pair of vector spaces are isomorphic? Okay, so you have to check that the following, which of the following are the isomorphic, means there exists a linear map from one to another, invertible linear map. And not one thing that if two spaces are isomorphic, then their dimensions should be same. It was done in the class, right? Because there is isomorphism. So it is 1, 1 and 2. So if T from V to W is an isomorphism, then dimension of V equals to dimension of W, right? And this is if and only if you can show that because these are all finite dimensional, if dimension of both the spaces are same, then they are also isomorphic. This was done in the class, I think. If and only if dimension are same, right? So just we have to compute the dimension of these examples, right? So let's come to the option number 1. R3 and P3R. It's given R3 and P3R. So what is the dimension of R3? Dimension, yes, 3. And what will be the dimension of P3R? What is
4.
What are the bases? Dimension of P3R is 4. Why it is 4? So you can see that P3R is the
1x square.
yes, 1x square and x cube. So as the dimension are different, so they cannot be isomorphic. So R3 is not isomorphic to P3R, right? So option number 1 is false. So let's check the second option. B and W are given. What it is? B is given the matrix Aij n cross n m2 cross 2 matrix such that A11 plus A22 is 0, right? And W is given R3. So what will be the dimension of B, right? So note that B, so what will be the, so if any element is in V, so it will be, suppose A is in V, then A will look like A11, A12, any 2 cross 2 matrix will look like this, right? A21, A22. But it's given that A11 plus A22 is 0. A11 plus A22 is 0, which implies A22 you can write it as minus A11, right? So you put it here, A11, A12, A21 minus A11, right? So then you can write it, how you will write it? A11, 1, 0, 0, 0, oh sorry, minus 1. Minus 1, this plus A12, 0, 1, 0, 0, plus A21, 0, 0, 1, 0. So, and these three are linearly independent, you can check in M2R. So dimension, and this is in B, right? So dimension of B is 3 because this is generated by 3 linearly independent. And what is the dimension of W? R3. And dimension of W and dimension of R3 is 3, right? So they both have the same dimension, means which implies B is equal isomorphic to W. So the option number 2 is true, right? Now check the third option. M n cross n and P m plus n. What it is? M cross n of R. What is the dimension of this? Dimension of M cross n matrices. So this has a dimension. It will be, dimension will be Mn, because 2 cross 2 matrices dimension will be, it is M cross n matrix, right? So like that, A11 dot dot dot, A1n dot dot dot, AM1 dot dot dot, AMN. So Mn number of independent coordinate are there. So dimension of AM cross n matrices is Mn. And what is the other one? Pm plus n. right? So what is the dimension of P? So you can see that this is spanned by 1 x square dot x to the power m plus n, right? So what will be the dimension? So dimension of P, m, and all these are linearly independent. So dimension of this is m plus n plus 1, because 1 is extra, 1 up to m plus 1, x1 to xm plus 1, and 1 is extra, so m plus n plus 1. So these two are not same dimension, which implies that m cross n r is not isomorphic to pm plus nr, right? Because they have different dimensions. So option number 3 is also false. What will be the option number 4? mn cross n and pmn. Option number 4. We have seen that for m cross n, we have seen that dimension is, we have seen this is mn, right? And what will be the pm dot n? This is m dot n plus 1, right? Dimension will be pm dot n of r, because it will be 1 will be more, because 1 is the 1 x square x to the power mn plus 1. So they have different dimension, which implies they are not isomorphic. Pm dot n, right? So option number 4 is also incorrect. Now Bm2 cross 2 matrix, this is symmetric matrix, this is anti-symmetric matrix W. So let's check option number 5. What it is given? B A m2 cross 2 such that A equals to A transpose, right? And W A belongs to m2 cross 2 such that A equals to minus A transpose. So what will be the dimension of these two space? So you can check that what is the general element, because A equals to A transpose, so the diagonal element, off diagonal element should be same. A is in B, which implies A should be of the form A11, A12. These should be same, right? A22, because if you take the transpose, then it will again be same. Then A transpose will be A. So what is this you can write, what is the number of independent vectors here? 1 0 0 0 plus A12 0 1 1 0 plus A22 0 0 0 1. So dimension of B is 3. And what will be the skew antisymmetric matrices? Now if B is in W, then B should be of the form diagonal element should be 0, right? 0 A12 minus A12 0, because if in the diagonal there is something, then if you take the transpose and inverse, it will not be same. So then you can write in A12 0 1 minus 1 0. So dimension of W is 1. So these two are not same. B is not isomorphic to W, right? So again this option is false. R5 and M2 cross 3 is this same? Option number 6. What is dimension of R5? This is 5, and dimension of M2 cross 3, what it is? It is 6, right? Because 3 times 2 is 6, which implies R5 is not isomorphic to M2 cross 3. So again option number 6 is false. Now the last option what it is? R10 and M2 cross 5. So option number 7 is what is dimension of R7? 7 or R10 is given. R10 it's 10, right? And what is the dimension of M2 cross 5 matrix? It is 5 times 2, it's again 10. So they are isomorphic. So R10 isomorphic to M2 cross 5. Right. So the last option is correct. Okay. So this is the last question. Okay. So assignment 4 is done. Is this fine? Okay. Any doubt? If there is no doubt, then let's stop for today. We'll meet in the next week in assignment 5.
Yes, sir. Thank you, sir.
Yes, bye.